NCM Learning Center.
Good morning friends. In this video we are going to discuss about the DC machines concepts. We know that the DC machines concepts are very important for all the competitive examinations. So when you are going to prepare the DC machines concept for competitive examinations, the 8 listed topics are very important. You should know these concepts. In the part 1 videos, already we discussed the part 1 videos. In that video, we discussed the lab and wave winding concepts, back EMF equation concepts, torque equation concepts, and the problems from these concepts. Okay. If you want that concepts, just go through the video. That video link is attached in the description box of the video. Okay. In this video, we'll discuss the types of DC motor and generator concepts and the problems from the types. In the next video, we will discuss the efficiency calculation of DC machines. Then in the part 4 video, we will discuss the remaining topics, okay, one by one. Okay. Now we will discuss the types of DC motor and generator and problems. The first type is DC shunt machine. We know the basic operation of DC motor and DC generator. Here the DC shunt machine means, here shunt means parallel. Here field winding and armature windings are connected in parallel. That is why it is called as DC shunt machine. Okay, DC shunt motor. So from the name itself, the equivalent diagram for the DC shunt motor is here. This is a field winding. This is armature. This is connected in parallel. For the DC shunt motor, input is electrical supply. So here this is the input. Electrical supply is given to the motor start to rotate. So here current, this is load current I. The current will divide into two parts. One is armature current, another one is shunt current. Now just apply the current law and voltage law, we can get the equation. From this equation we can find some parameters. Okay. So first apply Kirchhoff's current law here. Based on the Kirchhoff's current law, sum of incoming current is equal to sum of outgoing current. Here incoming current is I, outgoing current is IA and IS gauge. So I is equal to IA plus IS gauge. This is equation 1. Second, apply Kirchhoff's voltage law. In the armature, here brush are connected, some drop will be there, brush voltage. Here armature resistance, there is an armature resistance, so there is a drop by armature resistance. So just apply Kirchhoff's voltage law in this loop, so we will get V, applied voltage is equal to V. Here drop IA or A, armature resistance, drop by armature resistance, so induced EMF, so EB plus drop by brush. Okay, now we can apply the Kirchhoff's voltage law for its outer loop also. So V is equal to, here this loop, applied voltage is equal to V, drop, this drop, IS gauge into RS gauge. This is the equation for the DC shunt motor. So another one important parameter here for the shunt motor, field flux is constant. Because this voltage is constant, input voltage is constant. Here resistance, shunt resistance also constant. If voltage and current, if voltage and resistance are constant, then current will be a constant one. IS gauge will be constant. The field winding flux will be generated by the current. If the current is constant, field flux also constant. So pi directly proportional to current. So IS gauge directly proportional to flux by. IS gauge is constant, so flux also constant for DC shunt motor. So we know that torque equation and industry back EMF equation, T directly proportional to pi IA. So here pi also constant here. So T directly proportional to IA for the DC shunt motor. Induced EMF equations. So we write T1 by T2 is equal to IA1 by IA2. So we know that back EMF equation also. Back EMF is directly proportional to pi into N. Here pi constant, so E induced EMF directly proportional to speed, so E1 by E2 is equal to N1 by N2. So for the DC shunt generator, the equivalent circuit diagram here, field winding and armature winding are connected in parallel. Here DC generator, here voltage is generated at the armature side, the output will be electrical power. So output is electrical power for DC generator. Here armature current developed, this current will divide into two parts, IS gauge and I load current. So apply Kirchhoff's current law here. Incoming current is equal to IA, outgoing current is IL and IS gauge. So based on Kirchhoff's current law, IA is equal to IL plus IS gauge. The only difference is current direction. Okay, now apply Kirchhoff's voltage law for this loop 1. Here applied voltage is here induced EMF. This is applied voltage for the DC generator. But here shunt motor applied voltage is input DC voltage. Okay, B. Here input voltage is EB. So input voltage EB is equal to drop by armature resistance IRA plus drop by V plus then B. Okay. We can apply the voltage law for this outer loop also. So B is equal to IS gauge RS gauge. Same parameter here, field flux is constant because IS gauge constant. So D directly proportional to IA. So T1 by T2 is equal to IA1 by IA2. Similarly for E1 by E2 is equal to N by N2. This is the concept for DC shunt machine. The next second type is DC series machine. In DC series machine, armature winding and field windings are connected in series. So it is called as DC series machine. Now we will discuss the DC series motor. The equivalent diagram for the DC series motor is here. The field winding and armature windings are connected in series here. The resistance RAC, the resistance of the field winding is represented by the RAC because it is series winding. So it is represented by RAC. For the DC series motor, the input is electrical power. So this current is I. The current flow through the field winding, series winding may be represented as ISC. ISC means current flow through the series winding. Now we will represent the armature current IA. This all the currents are in series. So all are same. So I is equal to ISC is equal to IA. ISC means current flow through the series winding. IA means current flow through the armature. Okay. Now apply Kirchhoff's voltage law. Here apply Kirchhoff's voltage law for this loop. So here input is V, electrical voltage. So V is equal to this drop current flow, this voltage drop ISC RSC. In the armature, the drop, there is a drop, resistance drop IARA, then brush drop V brush plus back of EB. So we know that IA is equal to IAC. Substitute here, we will get V is equal to IA into RAC plus RA plus V plus EB. Because IA is equal to IAC. Okay. This is the equation for the DC series motor. Now we will discuss the DC series generator. The equivalent diagram is same that of DC series motor. Only difference is the current direction. Because in the DC series generator, the voltage is developed at the armature and this current flow from armature to load. So here this current is IA, armature current. The current flow through the field winding, series winding, it is represented as ISC. The current flow through the load is represented as IL. This all the currents are same because series. So IA is equal to ISC is equal to IL. Now apply Kirchhoff's voltage law in this loop. Here the input is back EMF EB, developed voltage. So based on the Kirchhoff's voltage law, applied voltage is equal to EB, EB is equal to drop. In the armature there is a resistance, so IARA drop, and in the armature there is a brush, so brush drop, E brush. The drop by the field winding is ISC RSC plus B. So substitute this equation, ISC or ISC, we will get EB is equal to IA into RA plus RSC plus V plus B. In the problem, if V plus is not given, the V plus value will be very small. It will be negligible one. If it is not given, we have to consider the V press value will be 0. Okay. Now, we know that field flux is directly proportional to the field current. Here, field current is varies. So, pi directionally proportional to ISC. Here, field current is ISC. We know that ISC is equal to IA. Substitute here. So, pi directionally proportional to IA. We know that T directionally proportional to pi IA. Substitute here the pi value here in this equation, will get torque is directly proportional to IA square, because pi is directly proportional to IA, already there is an IA, so we will get IA square. So torque is directly proportional to IA square for DC series motor. So T1 by T2 is equal to IA1 square by IA2 square. But in the DC shunt machine, pi is constant 1, so torque is directly proportional to IA. But this series machine, torque is directly proportional to square of the current, IA square. Okay. So we know that E is equal to, is directly proportional to pi I N1. Here pi is not a constant one. So E1 by E2 is equal to pi 1 N1 by pi 2 N2. Okay. This is the equation for the DC series machine. Now we will discuss the third type, DC compound machine. Here compound means series and shunt both are combined. Okay. For example, it may divide it into another two types. One is long shunt compound machine, another one is short shunt compound machine. Long shunt compound machine means initially the armature are connected with seriously connected with the series winding, then overall shunt windings are connected. So it is called as long shunt. The equivalent circuit is here. This armature and series field windings are connected in series, then combined parallel overall shunt windings are connected. So it is called as long shunt compound motor. It have both series and shunt windings, but initially it's series connection, then overall shunt connection. Okay. Now apply current direction and apply Kirchhoff's current law, Kirchhoff's voltage law. We can get this equation. For the DC motor, input is current, input is electrical power. So this I current is divided into two parts. This is ISH, this is ISC. But this current flows towards the series winding, so it is called as ISC. Okay. We may write this current is IA. From this diagram, we can say that armature current IA is equal to series field winding current ISC. Both are current series, so ISC equal ISC. Apply Kirchhoff's current law. Here incoming current is I, outgoing currents are ISH and ISC. So I is equal to ISH plus ISC. Now apply Kirchhoff's voltage law for this outer loop. Here input voltage is V. The drop this loop. Okay, this loop. So here ISC is equal to IA. So IA RAC plus IA RA P brush plus E. Then we may apply Kirchhoff's voltage law for this loop also, or this loop, anyone. So for this loop, V is equal to ISH RSH. Here flux, total flux, pi is equal to phi SH and phi SE. Here flux are not a constant one. Okay. Next we will discuss the long shunt compound generator. Same concept, same diagram, but the current direction only different. Here this voltage developed at the armature side, the current will flows from armature delivered to load. So this current is IA, then this current is ISE. The current will be divided into two parts, ISH and load current IL. So IS equal ISE, we are series, armature and series windings are series, so IS equal ISE. Then apply Kirchhoff's current law. Here incoming current is ISE, outgoing currents are ISE or IA, both are same. Outgoing currents are ISH and IL, so ISH plus IL, shunt current, load current. Okay. Now apply Kirchhoff's voltage law. Here input voltage is V. Okay. So V drop, V brush drop, armature resistance drop, This is the series winding resistance. IRSE plus V. Okay, we'll get this equation. Apply this voltage law for this outer loop, this loop. V is equal to ISH or SH. Total flux pi is equal by SH and by SE. Flux is in a constant one. So then we will discuss the short shunt compound machine. Short shunt compound means armature and shunt windings are connected in parallel. Then overall it is connected with series. For example, here the equivalent circuit diagram is here. The armature and shunt windings are connected in parallel. Then overall series windings are connected. This is short shunt, shortly shunted to short shunt. Okay. So here input is electrical power. So I load current. This current is ISE. This current further again it will divide into two parts. One is IA, another one is ISH. Here this load current and this series windings are not same. And in series. So I is equal to ISE. Then apply current in this junction. Here incoming current is ISE. ISE means I is equal to outgoing current is IA and ISH. IA plus ISH. Apply Kirchhoff's voltage law. This outer loop. This loop. Input voltage is V. V is equal to this drop ISRSE. This drop IRA. Armature resistance. V brush drop plus E. Okay. Motor have armature resistance drop, brush drop, and voltage induced voltage E. Now apply Kirchhoff's voltage law for this loop or this loop, anyone. Okay. This armature and shunt both are parallel. So this drop is equal to this drop. So we may write IRA plus V plus E is equal to this drop ISH or SH. Or just apply Kirchhoff's voltage law for this loop. We'll get V is equal to input voltage is V, drop ISRSE, then drop ISH or SH. This loop. Okay. Then total flux pi is equal by SH plus by SE. Short shunt. Then you will discuss short shunt compound generator. Same concepts, same diagram, but the current direction will be reverse. Here armature current will be generated initially. This current will be divided into two parts, ISH and ISE. This will be load current. This load current and series windings are series. So ISE is equal to IL. Apply Kirchhoff's current law in this junction. We will get incoming current IA is equal to outgoing current ISH and ISE. ISE means IL. Apply Kirchhoff's voltage law. This loop. Here input is B. Drop IRA drop, ISRSE drop, V brush drop, IRA, then B. We may apply this voltage law for this loop also. Is equal to IRA V brush plus ISH or SH. This loop. Okay. Total flux pi is equal to pi SH plus pi SE. This is the concept for compound machines. Next we will discuss the separately another one type, separately excited DC machines. From the name itself, the excitations field excited by separate source, so it is called as separately excited DC machines. For the DC motors, this is the field windings, this is armature. Field windings excited by separate source VF, armature winding excited by separate source VA. Windings have the inductive effect, so it is represented by inductance. This current is IF current, input this is IA current. But DC motor input is electrical, so this is IF. Okay. Here the inductive effect, the coils, field windings, coils are represented by the resistance and inductance, but here the inductive effect is zero, the reactance effect is zero because DC source. the inductance act as short circuits. So no need to draw the inductance here. Now here I is equal to IA, these are series. Apply voltage law here. VF is equal to IF RF. This top 0. VA is equal to IARA plus V brush plus E voltage. For DC separate excited DC generator, same concepts. But here field windings are excited by the source. So here current direction will be same. Field current direction will be same. This is excited. But here the armature current developed at the spot, induced EMF developed. This current will generate IA. This will goes to outside load current. So IL is equal to IA. Apply voltage law. VF is equal to IF RF. Here input voltage is E. So E is equal to V brush. The brush drop. Armature resistance drop IRA plus B. This is the concepts. For the separately excited machines, here the field flux VF is constant. VF is constant, IF is constant, so flux will be constant one. Same that of shunt machine. So we may write E1 by E2 is equal to N1 by N2, T1 by T2 is equal to I1 by I2, like that shunt machine. Okay. Next we will discuss two problems. Problem 1. This question is asked in gate question sound in examinations. The question in this question 120 volt DC shunt motor is given. It takes 2 ampere at no load and it takes 7 ampere at full load. The full load speed is 1200 rpm. Armature resistance and field resistance is given. We got to find the no load speed. Okay. So we know the circuit diagram, equivalent circuits for the shunt machines. Armature and field windings are connected in shunt parallel. The shunt field resistance is 240 ohms. Armature resistance is 0.8 ohms. Input 120 volt DC is given. At no load, it takes 2 ampere. Let me take this current is armature current IA. This current is shunt current IS. So we know this equation, KVL equation. V is equal to IARA, input is V is equal to IARA plus E1 plus brush. Here brush drop is not given, so the V brush value is 0. In this equation, V is given, but IA is not given, E1 is unknown, so we cannot find any parameters from this equation. So we know the another equation, the outer loop KVL, V is equal to IS gauge and RS gauge, this outer loop equation. V is equal to IS gauge and RS gauge. V value is 120 is given, 20 volt. RS gauge 240 is known. So from that we can find IS gauge value. Substitute this equation. We will get IS gauge value. IS gauge is equal to 0.5 amps. So IS gauge is known. By the case of current law at this junction, IA is equal to I minus IS gauge. Here incoming current I is equal to IA plus IS gauge. From that we can find this equation. Substitute here, we will get IA value. IA is equal to 1.5 amps. This is 1.5 amps. Substitute this parameter in this equation, we can get the E1 value. So here V is equal to 120 volt, IA is equal to 1.5, RA is equal to 0.8, E1 unknown value, brush value is negligible. V brush is not given, so it will be considered 0. So from that E1 value is equal to 118.8 at no load condition. Similarly for at full load condition, here at full load condition, read out the diagram. So at full load condition, it takes 7 amps. So same concepts here. So we can find the IS gauge value. IS gauge value will be constant 1. For DC shunt motor, IS gauge is constant, flux is constant, so IS gauge is 0.5 because input is constant. So the armature current IA value will be 6.5 amps. Okay. So substitute this IA value in this equation, we will get E2. V1 V is equal to 120, IA value 6.5, RA value constant 0.8 plus E2. We can get the E2 value. Voltage back EMF at full load speed, E2 is equal to 114.8 volt. Where full load speed is given, N2 is equal to 1200 RPM. We know that for the shunt machine, E1 by E2 is equal to N1 by N2 because field flux is constant. Substitute this equation, we can get the N1, no load speed. So, N1 answer is 1241.82 RPM. Okay, this is the answer. The conversion to speed, full load and low load speed is given, just use this formula, E1 by E2 is equal to N1 by N2 formula. Okay. Problem 2. This question is as in gate 14 examination. Here separately excited DC machine is given, no load speed 900 RPM, armature current is given, armature resistance is given, leakage inductance is given. What is the value of speed at full load? Okay. So first one is we know the equivalent diagram of the separately excited DC machines. Here input is 300 volt is given. At no load, armature resistance is 0.5. At no load, it takes 2 amps current. Okay, 2 amps current. So from that we can find just find E1 value. VA value is given, IA value is known value, IA is 2 amps, RA is known value, brush is not given. So it will be considered 0. So substitute here, we will get E1 value. E1 is equal to 299 volt. At no load, the speed is 900 RPM. We have to find the full load speed. At full load, at load condition, it takes 15 amps. Just find the E2 voltage. Here VA 300 volt, IA value is 15 amps, RA armature resistance 0.5 ohms, plus voltage is not given, E2. Just find E2 value, E2 is equal to 292.5 volt. For separately excited machine, field flux is constant. So E2 by E1 is equal to N2 by N1. Substitute these values, we can find the speed at loaded condition. So N2 is equal to 880.43 RPM. Now do it yourself. 4 questions are listed. The first question is asked in IES 2020 preliminary examinations. The second question is asked in GATE 2021 examination. Third question is asked in GATE 19 examination. The fourth question is asked in TRB 2017 examination. The answers for the question is, for the first one, option A is correct. For the second one, 275.18 RPM. For the third one, 219. For the fourth one, option C is correct. If you have wrong answers or mismatched answers, just post your doubts. Our NCM Learning WhatsApp group. Use our NCM Learning WhatsApp group. You can get the good marks in the combat examinations. Okay, good. Thank you.
Thanks for watching. Click the subscribe button and hit the bell icon for notification. Like, comment and share.